Thank you. Welcome to our Friday seminar. And today we have a Ph.D. student that graduated from our civil engineering program. And Alex, actually, he presented a year ago. And so today we're going to have final results related to his dissertation. And Alex is going to be a tenure-track faculty position at University of British Columbia, Vancouver, Canada. So congratulations to Alex, and it's a great achievement. And let's go. And don't forget to sign.
Thanks, Miguel, and thanks to you all for coming out. As Miguel mentioned, I presented about a year ago on kind of the early results for my dissertation, and now we're bringing it back around. So I'm going to do some of the setup, but I'll move through that a little faster on the background and methods, and then focus on the later results and some of the applications that I looked at. So the topic is bicyclist uptake of traffic-related air pollution, and then I put the subtitle in there to emphasize that I'm focusing on kind of takeaways for people, for transportation professionals and for travelers as well. And before I move further, I'd like to thank Miguel, who is my advisor and co-researcher on this project and on my dissertation committee, as well as Jim Pankow and Wentai, who are over in environmental engineering and chemistry, who are also researchers on this topic as well. So if you've seen me talk about this before, you've seen this slide. This is the framework I like to use to get everyone on the same page, both in terms of verbiage and as well as the steps connecting transportation emissions with health outcomes for travelers. So we can think of it as a 6-step process. So motor vehicles emit a number of air pollutants and precursors to air pollutants. And then we have atmospheric processes that lead to a level of air quality around a city. And then if we know how, when, and where people travel around the city, we can start to look at their exposure concentrations. So that's the concentrations in the air that they're going to be breathing in while they're traveling. And then to take it farther, we need to think about not just what's in the air around them, but how much they're actually inhaling and intaking into their bodies. And we call that inhalation dose or intake. Then to go a step further, not everything you breathe in stays in your body. So the risky stuff is the stuff that you actually absorb into your body, and we call that uptake dose. And then finally, it's the amount that you absorb, the uptake dose, that will ultimately lead to the negative health effects, depending on how your body responds to that, the dose response function. So in my research, I focused on steps 3, 4, and 5. So that's what we're going to be talking about today, is exposure, inhalation, and uptake. So a little bit of background. Up to, say, mid-2014, there have been a little over 40 published studies that have measured bicyclist exposure concentrations on road. That's anywhere in the world, and going back to the earliest ones were in the 1970s, but the vast majority have been in the last 10 years as there's been a resurgence in interest in urban bicycling. So here are a number of different pollutants that have been measured. I'll call your attention to VOCs, or volatile organic compounds, which is actually a whole class of compounds that we call VOCs. They're traffic-related, but they're also related to industrial sources as well. Carbon monoxide, CO, that's another one we're going to be talking about. That's strongly traffic-related. And then you have several different types of particulate matter, or PM, stands for particulate matter. So you have PM classified by size, as well as black carbon, which is classified by type. It's essentially soot. Right? So there have been a number of different pollutants studied in terms of bicyclist exposure concentrations. But a little more than half of the studies have really focused on the question of modal comparisons. So the core study question was, which travel modes have the highest and lowest exposure concentrations? And this is interesting from a kind of a scorecard point of view, but it doesn't provide a whole lot of information for transportation professionals about mitigating travelers' air pollution exposure, other than encouraging mode shift to one mode or another. But there has been a lack of analysis of the intramodal determinants of exposure concentrations. In other words, what are the roadway characteristics and travel characteristics that lead to higher or lower exposure concentrations for someone who's already chosen a certain mode? But if you're interested in the scorecard results, when you compare bicyclists to other modes, the exposure concentrations really depend on the context in which the study was conducted. So if you have bicyclists on separated paths, bike ped paths in parks, for example, it's going to be a lot lower. But if you have bicyclists in mixed traffic on road, it might be a little higher because they don't have the vehicle shell to protect them. But the results of these kinds of studies are pretty varied in terms of who has higher exposure concentrations. One of the determinants of exposure concentrations that has been studied in about 10 of the studies was high traffic versus low traffic routes for bicyclists. So here they would have a prescribed route, which would be along higher volume, large traffic roads, and then another route along low traffic roads, sometimes an off-street path. And there can be some pretty high exposure differences depending on the type of pollutants. So some pollutants are more related to the traffic levels than others. Some have higher background concentrations. Some have longer or shorter lifetimes in the atmosphere. And so it does depend on the type of pollutant you're looking at, but more strongly traffic-related compounds or pollutants, you're going to see some pretty large differences between high traffic and low traffic routes. So that's about exposure concentrations. But remember, if we think back to the steps involved, that's only about halfway up to health effects. We still have to think about how much people are inhaling and how much they're absorbing into their bodies. So that's where ventilation comes in. So here I'm talking about human ventilation, or essentially breathing. And the more you're breathing, the larger doses you're going to be inhaling into your body, which makes sense. And breathing, as you know, is connected with exercise or physical activity level. And so this is a kind of a representative sketch of how ventilation, in terms of volume per unit time, or liters per minute, is related to power output. So the amount of energy you're putting into bicycling, for example. So the harder you're working, the more you're breathing. And as a consequence, the more active travelers are going to be inhaling a larger mass of pollutants for a given exposure concentration. So the survey of the literature revealed that about 2 to 5 times higher ventilation rates are expected for bicyclists versus people who are not active travelers, so people in a motorized mode, either in a car or a bus. Generally about 2 to 5 times higher. So if the exposure concentrations were similar, bicyclists would be inhaling about 2 to 5 times larger masses of air pollutants. And the result of that, before I said the exposure, if you look at modal comparisons of exposure, it's kind of a mixed bag. Sometimes it's higher or lower for bikes. Once you go to inhalation doses, it's consistently higher for bikes than people in motorized modes. And then pedestrians also have elevated breathing rates or ventilation rates. So they also tend to have higher inhalation doses than people in motorized modes. So looking at how this has been assessed in the literature, if we broaden our scope to think about not just the studies that have directly measured bicyclist exposure, but also ones that have modeled it in some way, there have been 57 studies that assessed bicyclist air pollution risks in some way. Of those, 38 ignored the ventilation question, so they're just looking at exposure. Of the ones that considered ventilation, 16 of them assumed a constant ventilation because they're really only interested in modal comparisons. So they say, well, bicyclist breathing rates, we're going to say, are 2.8 times higher than motorists, and we're just going to make a factor adjustment like that. And then three studies have considered the fact that bicyclist ventilation rates vary on road. 2 of them model ventilation, and only 1 has directly measured ventilation using face masks for bicyclists. So they did consider the fact that depending on how and where you're bicycling and how hard you're riding, your ventilation rates can vary quite a bit. So clearly a lack of analysis here of how ventilation rates vary, which is one of the big determinants of inhalation doses. Okay, so going one step past inhalation, now talking about uptake doses. Here we have even fewer papers in the literature to rely on for quantifying bicyclist uptake doses. So there have been 2 studies that use biomarkers looking at absorbed doses of different pollutants for bicyclists. One about 15 years ago in Italy looked at urban bicyclists versus rural bicyclists and found that urban bicyclists had absorbed more VOCs. So they took blood and urine samples and found more markers of absorbed VOCs. And then another study just a few years ago in London was looking at black carbon deposited on the upper respiratory tract of bicyclists and transit riders, and found more black carbon had been deposited in the lungs of, or the upper respiratory tract of bicyclists versus people in transit. So we're starting to quantify this, but very few studies, and again, not a whole lot of information for transportation professionals to take this information and then try and quantify the differences in some sort of change we want to make in the transportation system. So into that context, into that chasm, we decided to jump with this research. And so my dissertation asked two main questions. The first was about quantification. So how does uptake of air pollutants for urban bicyclists vary with different roadway and travel conditions? So in other words, what are the transportation system impacts on bicyclists' pollution uptake? And then secondly, the extension of that, what transportation-related strategies can we use to try and reduce bicyclists' uptake? Right? So first quantifying it, and then what are the takeaways for smarter transportation systems? So how do we go about doing that? Well, first, we did take more direct uptake measurements than just estimating it from exposure concentrations. And the technique we use is called breath biomarkers. And this is a technique that comes out of the medical sciences, and it's been used a little bit in occupational exposures, but this is the first time someone's tried to apply it for travelers. So this is a pretty new approach to trying to quantify this problem. And the way it works is that for certain types of compounds, for certain types of pollutants, the concentration in your exhaled breath is closely representative of the concentration in your bloodstream. So you can collect samples of people's exhaled breath as a proxy measurement for the concentration of those compounds in your bloodstream. So it's a really non-invasive way of getting measurements of concentrations in a biological medium. So these are called breath biomarkers. And what we did was we collected these exhaled breath samples at before a ride and then periodically over the course of a ride to look at how the breath concentrations changed with travel and exposure and roadway conditions. So we put some bicyclists out on the road. We had them ride around in Portland. We had an instrumented bicycle. Here's a photo of it. There's several different GPS devices measuring location. We had cameras for visual of traffic conditions. We had a number of continuous air quality and meteorological instruments, temperature, humidity, total VOCs, carbon monoxide, fine particulates. And we were also taking samples of whole air onto carbon sorption tubes to do more detailed gas analysis at the laboratory. And then we had bags to collect these breath samples for the bicyclists periodically over the course of the ride. In addition, to look at the physiology question, or the ventilation question, we used, it's called a bioharness. It's a physiology monitoring strap. It's worn around the chest, and it measures heart rate, but it also can measure ventilation rate because it measures expansion of the chest cavity. So you can get a waveform from which you can deduce the ventilation rate. In addition to that, what we did is we used, it's called a spirometer, so you can measure the breath volume. So we took spirometer data before and after each data collection to connect the breath amplitude with a tidal volume or breathing volume. So that allowed us to make fairly direct on-road measurements of ventilation rates while you're traveling. So this was an alternative to the face mask method, which obviously wearing a face mask is going to preclude you making uptake measurements, right? Because it's going to affect the amount of pollutants you absorb. So this is a non-invasive way of collecting physiology data during riding. So part of the research was also to validate that method, because that's also a new approach. So we had prescribed sampling routes. We put the riders out on the road. We had routes of about 20 to 30 minutes that were designed to be along similar facilities. And we would take a breath sample before this segment. So here's an example where, starting at Mount Tabor Park, take a breath sample, ride along local roads for about 3 to 5 miles, so about 20, 30 minutes, and you take another breath sample at the end. So you can look at the change in breath concentration as a function of the exposure and travel conditions for that segment. And then that post-breath sample became the pre-breath sample for the next riding segment. So here's a riding segment along major arterials. So you take a pre-breath sample there, right along the arterioles, take a post-breath sample at the end. Right? So periodic breath samples, and then exposure conditions during riding. This is the whole sampling domain. You can see the roadways that are drawn with colors there are the roadways where we collected data. We had a total of 74 breath samples, collected data over 9 days in 2013. Got about 40 hours of on-road data. And you can see we had a range of facilities. So the yellow ones are, I'm supposed to use the mouse. The yellow ones are off-street paths. You might recognize the I-205 and Springwater bike paths. And then we had some local roads, bike boulevards, all the way up to major arterioles like Foster, Powell, and Barber Boulevard. So tried to get a really wide range of facilities around the city. And then once we collected all that data, the next step was model development. So we developed a series of models, starting with first exposure concentrations as a function of roadway, travel, and weather conditions. And then the next step was looking at modeling ventilation rates as a function of energy expenditure or power output while bicycling. And then the third step, the most ambitious piece of the modeling, was to model breath concentrations. First, going one step back, looking at breath concentrations as a function of exposure and ventilation, and then trying to go one step farther backwards or up the causal pathway and looking at how breath concentrations are dependent on weather, traffic, and roadway conditions. So weather and traffic, roadway affect exposure and ventilation, which in turn affect absorbed doses of VOCs. So trying to make that whole connection. So that's what we did, and here's what we found. So first, in terms of exposure effects, these are just, I decided not to put the regression model results up there, so these are just kind of the big takeaways. So first of all, we found about a 2% increase in VOC exposure concentrations per 1,000 ADT, or average daily traffic. This was robust to a number of different model specifications, and actually it was very similar for CO as well, carbon monoxide as well. So this is a really handy quantification. It's something that was not in the literature yet, and this provides a pretty easy way to do some back-of-the-envelope or kind of scenario planning estimation of exposure differences for two different routes, because you estimate about 2% higher exposure per 1,000 ADT difference in the two facilities. We had high-resolution data, so we also had some very detailed traffic and travel characteristics. One of the things that we found is that exposure concentrations are about 20-30% higher in stop-and-go riding, meaning when you're stopped and when you first start to accelerate and when you're in low-speed riding situations. And that's reflective of the influence of being in a queue and also being at intersections. So stop-and-go riding was about 20-30% higher. And then in terms of off-street paths in general had exposure concentrations that were similar to small street, about 1,000 ADT. However, there's an industrial corridor that the Springwater goes through down in the southernmost part of it, and in that corridor, concentrations were 300% higher for VOCs. And here's a visual of what that looked like. There's a number of heavy industries around there, metalworking industries, for example, that are known emitters of VOCs. They're registered with the EPA. And you can see, so the height of these dots, or the height of the pins, is the concentrations on, this is just one day where we sampled along that route. And you can see really high concentrations. Now this is pollutant dependent. So there are industries down there that are known emitters of VOCs. If you look at the same data for CO, it's not much higher in that corridor, because CO is more strongly tied to traffic than industry. If you look at PM 2.5, that also is higher through this corridor, because industry is also an emitter of PM 2.5. So this is pollutant-dependent results. But one of the findings is that off-street paths, depending on surrounding land use, not always low exposure facilities. We also did some side-by-side comparison of parallel routes that were separated by one block. And here we see 3 of those. So this is Burnside-Ankeny, Williams-Rodney, and NATO, and the Tom McCall Riverside Path. Probably most of you are familiar with these locations. And we found large, statistically significant differences in exposure just by going one block off route. And you can see for carbon monoxide and VOC concentration differences were quite large between the kind of larger traffic facility and the smaller traffic facility. So that was exposure model results. In terms of ventilation, looking at breathing rates as a function of how hard you're riding, essentially. We found increases of about 4 to 8% per additional 10 watts that you're putting into bicycling. And this is consistent with the literature. It's also consistent. It's similar to data we collected for the same subjects on an ergometer or a stationary bicycle. So we had them riding a stationary bicycle. Similar, but actually slightly lower for all 3 subjects. And so the takeaway there is that the dynamic response seems to be a little bit smaller than the steady state response to exercise. And there's also some support for that in the literature. So in other words, if you're just bicycling at a constant 100 watts versus a fluctuating power output that averages 100 watts, the ventilation response is a little lower if it's a dynamic workload. Also, if we're going to look at, this is interesting for hotspot analysis, the mean lag between a change in your power output or workload and the change in your ventilation rate was about 50 seconds. And so that means that when you have a change in workload, or say you put in a lot of energy for an acceleration event, the breath response or the ventilation response isn't immediate, but it's spread out over the next 1 to 2 minutes. So what that means is if you're looking at hotspots in the network, for example, an intersection, which tend to have higher exposure concentrations, they also tend to have higher workloads for bicyclists because they'll accelerate from a stop. But that acceleration event influences ventilation for 1 or 2 minutes down the road, not immediately. So it's kind of good in terms of the intersection effects because the exposure and the ventilation are separated in space a little bit. Conversely, if you think about someone stopped at an intersection, their workload is 0, but they're breathing with the ventilation of the last 1-2 minutes of their trip. So you have to think about, if you're looking at in detail and you're thinking about like where are the inhalation dose hotspots on our network, there's a 1 to 2 minute lag between your workload and your breathing rate. Okay, and now getting to our breath concentrations. So first of all, I was excited because it worked. So I was able to do something with the data. So we found that breath concentrations were larger on higher traffic facilities and where exposure concentrations were higher. And that's good. So for example, if we compare everything, normalize it to concentration at a park location, exposure was higher on higher traffic facilities and breath concentrations were higher as well. But the breath concentration response was muted or smaller than the exposure differences. So the elasticity between the two in the model results, I'm not sure if I have the slide on there, but is elasticity of about 0.5, which means that if you have a certain change in your exposure concentration, the change in your breath concentration is about half as large. So we quantified about 75 compounds in the air samples that we took. Of those, about 25 were consistently quantifiable in both the breath and the exposure air of the bicyclists. Of those 25, 8 worked as what we'll call biomarkers of traffic exposure. In other words, for 8 of the compounds that we measured, changes in breath concentrations were significantly associated with changes in exposure, which were related to changes in traffic conditions. And these were all aromatic hydrocarbons, which are known to be related to motor vehicle fuels. So it's not surprising that these were significant. However, I just wanted to point out some of the reasons why not all the compounds work. I couldn't do this for every VOC that we measured. And there's a number of issues for trying to do breath analysis for exposure biomarkers. One of them is background concentrations. So we all have this background level of VOCs in our blood that's a function of where we've been for a while in the past. Living in a city, there's a lot of different exposures. There's also in-home exposures. If you have a garage attached to your house, you essentially have a car in your house that is always emitting a little bit of VOCs. So there's a lot of background issues. There's also endogenous production, which means that your body produces some compounds through metabolic processes. You're just going to be off-gassing some compounds. And even if it's a small even if it's much smaller than your exposure, it's more noise in the data, right? That makes it hard to pick up the signal of traffic exposure because it gets kind of noisy. And another factor is high water solubility. So your breath, as you might expect, has a lot of moisture in it, and certain compounds that will partition into the water vapor in your breath, you'll get some losses, and then that also makes it the data more noisy, so harder to detect the signals. But the good news is there was about 8 compounds that worked as biomarkers. And then I talked about modeling breath concentrations as a function of exposure and then going back a step to traffic and roadway conditions. So if we look at breath concentration as a function of measured exposure and ventilation, we found that a little less than half of the variance in breath concentrations was explainable with our measured exposure and ventilation. Right? And that reflects the fact that, like I said, there's a lot of other processes going on, so there's a lot of noise. So we were able to explain about half of the changes that we saw in breath concentrations with this information. If we look at modeled exposure and ventilation, in terms of modeled from roadway traffic and weather variables, it turns out the loss in explanatory power was only about 10% compared to when we directly measured exposure and ventilation. So that's pretty good in terms of our roadway traffic and weather variables are pretty strong determinants of the explainable portion of breath concentration changes. So there's other physiological things that are influencing breath concentrations. But the part that we can explain with exposure and ventilation, roadway traffic and weather variables are pretty strong determinants. And if we split it apart by roadway and traffic versus weather, roadway and traffic were slightly more than half of that explained variance. So roadway and traffic variables are measurably impacting our breath concentrations of these VOCs. Okay, so that's the sciencey part where we collected data and did statistical analysis. So now the last chapter is looking at how can we use the information there to provide more information and guidance for transportation professionals to make healthier bicycle facilities, and for travelers as well. So like I said, we modeled ventilation as a function of power output or workload while you're bicycling. We can take a step farther back because we can calculate workload using a physical equation of the bicycle and look at how workload is affected by things like rolling resistance, aerodynamic drag, grades along the route. And here's an example of, for different steady-state bicycling speeds, how the workload changes with the speed. As you can see, it's clearly a nonlinear relationship. So you have aerodynamic drag increases quite a bit at higher bicycling speeds. And then if we take that and combine it with our ventilation model, then we could develop relationships like this. So here what we're looking at is the ventilation rate now per unit distance for different steady-state bicycling speeds. So here on the horizontal axis is a cruising speed for a bicyclist, and the vertical axis is the volume of air inhaled in liters per kilometer, so liters per unit distance. And the reason we're doing it in distance instead of time is because that's more representative of what would happen over a trip, right? Because you make trips primarily based on distance. And then the two lines here show the ventilation rate per unit distance as it changes with speed for a couple of different grades. And clearly nonlinear relationship, and it actually has a minimum that's well within the range of reasonable bicyclist speeds. So here for a 0% grade, we see that around 11 miles an hour is what we can call the minimum ventilation speed. So in other words, if this bicyclist is cruising at about 11 miles per hour, then they're going to inhale the smallest volume of air for their trip, and as a consequence, inhale the smallest dose of pollutants for a given exposure concentration. If we look at the 2% line, we see that at a higher grade, you're breathing more, so you're inhaling more in general. So you'd expect that because you're doing more work. But what's interesting is that the minimum point on the curve is slightly to the left. Right? So the higher the speed, the lower your minimum ventilation speed is going to be. And of course, these curves are illustrative for a certain bicyclist. It's going to depend some on the weight of the bike, the amount of cargo you have, your frontal area, the weight of the bicyclist, things like that. But for this illustrative bicyclist, here are the results. And we can connect these minimum points to develop what I'll call the minimum ventilation speed curve. So here you see is basically plotting that minimum ventilation speed, so the low point on the previous curve, for different grades. And like I said, you can see that it starts around 11 miles an hour flat, and then the steeper it is, the slower your optimum speed is from an inhalation dose point of view. Kind of makes sense. And it kind of corresponds to what bicyclists do, right? Because they're going to slow down because it requires more energy to maintain speed on a grade. We can also look at the effects of stops along a route on ventilation rates. And what we're looking at here is, on the horizontal axis, I have a range of cruising speeds. And on the vertical axis, I'm showing the inhalation penalty of coming to a stop and then accelerating back up to your cruising speed, not counting any stop time. So this is basically a penalty associated with the extra time it took to do that, as well as the extra energy it took to accelerate back up to cruising speed. This, by the way, is assuming that you're braking to decelerate and you're not riding a fixed gear and putting in more energy to decelerate. So if you're braking to decelerate. And I've put it in units of cruising equivalent excess ventilation, which means this is the ventilation penalty put in units of distance. So what we can take away from this is, for example, in Portland we have about 250-foot blocks. And so you can see that if you have a cruising speed of about 13 miles an hour, each additional stop on your trip leads to excess ventilation of about 1 block of bicycling. So every time you have to come to a stop, you're breathing in 1 block's worth of inhalation dose, if that makes sense. So you can use this kind of information to quantify the benefits of things like flipping stop signs on a bike boulevard. So every bicyclist that doesn't have to come to a stop there, you have saved inhalation volume. In terms of routing, if we think about the parallel path comparison like I talked about before with the exposure data, if we're looking at when it's worthwhile to go out of your way to use a lower volume facility. So you go out of your way, you're going to have a longer trip distance, you're going to have a longer exposure duration, but you're probably going to have a lower exposure concentration. So there's a trade-off there because you're longer trip but lower exposure. So what's the trade-off in terms of inhalation dose? Well, we can calculate that, and from our data, going 1 block out of your way to take a low-volume street and then going 1 block back over is worth it if you're going to bike just 1.6 blocks on a major arterial or 4.3 blocks on a minor arterial. Meaning, as long as your route is at least 4.5 blocks long on a minor arterial, you're better off from an inhalation dose point of view going out of your way to use a lower exposure facility. And so these are the kind of trade-offs we can think about when quantifying exposure differences in bicycle network planning. So we took this information, which is looking at trade-offs for a rider in terms of inhalation dose, and thought, well, how does this compare to what bicyclists actually do? Right? Because we know bicyclists like to avoid traffic, and they will tend to go out of their way to use a lower traffic facility. So the question was, does their tendency to avoid traffic and go out of their way naturally minimize their inhalation doses? Or is there some disparity there in how far people will go out of their way? So what we did was compare those trade-offs I was just talking about with the results of a bicycle route choice model that was developed here at Portland State, actually by Jennifer Dill, Joe Broach, and John Glebe. So they had bicyclist routing data, and they did regression analysis to quantify people's willingness to trade off distance versus higher traffic facilities for different types of comparisons, bike lanes, no bike lanes, et cetera. So we took that data, compared it with our data, and looked at when they were in balance and when bicyclists were willing more or less willing to trade off distance for exposure to traffic. And what we found is that if you look at a bike boulevard or a neighborhood greenway or a similar low traffic street and compare it to a bicycle lane, if that bicycle lane is on a collector street, about 6,000 to 10,000 ADT, then it's a pretty good balance. Bicyclists will tend to kind of naturally minimize their dose by making appropriate trade-offs from an inhalation dose point of view between extra distance and exposure to traffic. But if we look at a bike boulevard and a bicycle lane on a larger facility, a minor or major arterial, bicyclists aren't willing to go as far out of their way as might be optimal from an inhalation dose point of view. So we could say that bicyclists will slightly under-avoid arterials in comparison to the inhalation dose minimizing route. On the other hand, if we look at a minor arterial with no bicycle lane on it, bicyclists really don't like that. And so, excuse me, bicyclists are willing to go more out of their way to avoid a minor arterial with no bike lane on it. And in that case, bicyclists will slightly over-avoid this facility. In other words, bicyclists are willing to go farther out of their way than would be necessary for an inhalation dose minimizing route. Right? And you might have a situation where bicyclists are actually increasing their inhalation dose because they're going so far out of their way they have a very long trip duration. And if you compare a bike boulevard to a major arterial with no bicycle lane, bicyclists will go way out of their way to avoid this facility, whereas the inhalation minimum path might be along the major arterial. Of course, I'm not saying the bicyclists are making bad decisions in any way. We're just comparing their preferences with inhalation doses. So bicyclists make route choice decisions on a lot of factors. This is just one consideration. Okay, and pretty much right at the beginning, I was talking about people exercising on city streets and as a result breathing in more air pollution. So I wanted to tie that back around and look at how uptake of traffic-related air pollutants is dependent on exercise level. So as I said, bicyclists' inhalation rates tend to be about 2 to 5 times higher than people in non-active travel modes. So they're breathing more. As a result, for a given exposure concentration, their inhalation rate is 2 to 5 times higher. Because the ventilation rate's higher, inhalation rate's higher, about 2 to 5 times. From the exposure science literature, we know that PM uptake doses will be slightly higher than that, depending on the size of the particulates. So if inhalation rates are 2 to 5 times higher, PM uptake rates are at least 2 to 5 times higher. Okay? So exercise is pretty bad from a PM uptake point of view. On the other hand, for VOCs, uptake is not proportional to ventilation rate. And that's because there is a blood-air equilibrium condition at which point you don't continue to absorb additional VOCs beyond what you're metabolizing out or that's absorbing into other body tissues. So the uptake of VOCs is limited by this equilibrium condition. And the equilibrium condition increases with exercise, but the result is that when you're exercising on a city street, VOC uptake is only about 1.5 to 2 times higher than if you weren't exercising. So ventilation rates are higher, inhalation rates are higher, uptake rates are higher, but for VOCs, they're not quite as high as they appear to be from an inhalation dose comparison. So there's a little bit of good news for people using active transportation, at least for VOCs, not for PM. Okay, so here are some conclusions. So in this research, in terms of research question 1 or research question 2, we quantified a number of determining factors for exposure, ventilation, and uptake. We talked about ADT, stop-and-go riding, industrial corridors, speed and grade, how those all influence exposure and ventilation, which in turn influences uptake rates, or absorbed VOCs. And those quantifications led to specific mitigation strategies such as bicycle routing along low-volume streets, making certain travel speed choices to minimize inhalation doses, reducing stops, and the benefits of separated facilities for bicyclists as well. So some takeaway principles, if you're not that interested in the science of how pollution is uptaken by people traveling around, these are just kind of some ideas that you might want to think about when you're thinking about bicyclist uptake and all the complicating factors that go on. First of all, in terms of bicyclist exposure, traffic-related air pollution is not a thing. It's not, there's not one thing that goes up or down. Traffic-related air pollution is composed of lots of different pollutants. And they all have different emissions rates, they have different sources, they have different lifetimes, they have different risks. They have different methods of absorption by the body. And so it's important to remember that it's very common to have a change in a system that will lead to an increase in one pollutant and a decrease in another pollutant. And it's not always easy to assess the net trade-off of those because we don't have the same amount of information on all these different pollutants. So that's one thing. Traffic, weather, and land use are all important factors for bicyclist exposure. It's not just one or the other. And so, and this is reflected in, for example, the off-street path through an industrial corridor, extremely high exposure to some types of compounds. So it's important to remember that all three are, I didn't really talk much about weather, but wind speed has a huge influence on exposure concentrations on road. Temperature as well can have a big influence on certain types of pollutants. Third, there's some clear benefits, though. All that aside, there's a lot of uncertainty, but there's also some clear benefits of separating bicyclists from traffic, both for riders themselves and for transportation system planners who are deciding where to locate bicycle routes. In terms of inhalation, on-road inhalation varies greatly. We have a 2 to 5 times rule of thumb range, but for any given bicyclists, that's a huge range over which your ventilation can vary on road. And as a result, bicyclists don't just have this one ventilation rate. It's a wide range, and that has a huge influence on the amount of pollutants that you actually breathe in. And then dynamically, the breath response, as I said, is spread out. It's not immediate. Finally, in terms of uptake, particles are highly sensitive to the breathing rate, which, like I said, can vary quite a bit depending on how you're riding. But for some gases, they're not quite as sensitive to breathing rates, so then travel duration becomes more of an influence relative to particles. Taking that information and the other information I've talked about today and thinking about a number of different bicycle facilities, this is some takeaways in terms of design consideration for bikeways facilities. And this goes back to some of the initial motivation we had for this research, is that in the design guidance for the latest bicycle master plan, one of the appendix J or K or P or something, there was no mention of air quality or pollution exposure as an explicit consideration, and which is understandable because there's fairly limited information out there. But this is our kind of summary of some of the considerations for different bicycle facilities about air pollution risks. So if you have a bicycle lane, unfortunately bicycle lanes tend to be on fairly high traffic streets, so exposure concentrations tend to be higher than the other bicycle facilities. But there is some lateral separation, which can help reduce exposure concentrations. And then having a dedicated lane reduces the duration that a bicyclist would be around traffic congestion, and also allows them to jump queue at intersections. And so having a dedicated lane can have some inhalation dose effects. Like I said before, 20 to 30% higher during stop-and-go riding. Bike boulevards or neighborhood greenways, these are on low-traffic streets, so that's good from an exposure point of view. There are additional benefits from traffic calming on these facilities, so the lower the traffic volume, the lower the exposure concentrations. And then we also know that fewer stops reduces the inhalation dose, whatever the exposure concentration is. So there's some benefits of, like I said, flipping stop signs, for example. A cycle track, also like a bike lane, tends to be on higher volume facilities than bike boulevards, but you have additional lateral separation, which has measurable benefits in terms of exposure concentrations. And once again, fewer stops will reduce the amount of uptake. And then finally, for off-street paths, these are generally low exposure routes. Even the I-205 bike path is a fairly low exposure concentration. However, there are some spots where they can be extremely high depending on the surrounding land use. And once again, fewer stops, fewer pollutants uptaken. So some of the next steps, this was, what I just talked about was it's about 3 years of my life and our lives. So it's a lot that went into this, but there's still a lot to be done. There's still more to be done to abstract the information, kind of like I was talking about there in terms of takeaways for health impact assessments and cost-benefit analyses for transportation, bicycle transportation. There's additional biomarkers that can be studied, and I'd like to undertake some of that. I talked quite a bit about ventilation and physiology, and so there's more work that needs to be done characterizing urban bicyclists, things like speed choice, things like frontal area and mass and rolling resistance that will allow us to get better quantifications of workloads while bicycling and, as an extension, ventilation rates for bicyclists. It's a pretty natural extension, I think, to take this study approach and extend it to pedestrians, which is the other group with elevated breathing rates on road. And then lastly, I'll mention crowdsourced air pollution data for active travelers is something that I'm very interested in looking at. And as I actually have it with me today as kind of a side project throughout this research, I've been working on what I'm now calling the SPEC, so Sensing Pollution Exposure by Community. It's a small, portable, lightweight device, has a battery that charges just with a USB cable, and it has not gold standard accuracy, but it has enough resolution that you can kind of do surveys to get a pollution map looking for hotspots around the network and assessing differential pollution risks on different types of facilities. There's a custom app I wrote for it, and there's a screenshot from that where you can see mapped gas concentration for one trip. And so we've got that up to the point where it's streaming some data, but it's still in the prototyping phase. But there's a lot of interest in this. There's a number of researchers around the world that are working on these low-cost personal air pollution sensors. This is just one example, but I think this is an exciting area where the field is going to try and get much more data, because the data is hard to collect. There's not a whole lot of it out there. So if we can start to do this, then we can really get a better picture of what travelers' exposure concentrations are. Big data. And with that, I will wrap it up and ask if you all have any questions.
Who were the 3 subjects?
They were 3, you mean like, demographic-wise, yeah. So they were all 3 healthy. We have a respiratory disease questionnaire to make sure that no one had any respiratory diseases. And they were all moderately fit, 20s, 30s, 40s, 2 male, 1 female. And the idea there was not to get a population-wide picture, but to try and see if the uptake rates were similar amongst the 3 subjects. And I don't think I mentioned that, but in the regression analysis that we did for breath concentration as a function of exposure, the coefficient was not significantly different among subjects. And so we found that it was consistent amongst our 3 subjects.
I'm just curious, you perform the regression analysis, right?
Yeah.
So what kind of regression you use? Because this data must be really dependent. Because whenever you're dealing with pollutant data, there is an dependency issue. So what kind of analysis did you perform? Like what kind of regression did you perform?
Yeah, good question. So there was a number of different ones for the different steps. So the last one was a multi-stage least squared, and earlier ones were exposure was least squares regression, controlling for heteroscedasticity and autocorrelation. And then for the VOCs, actually did a panel data regression model. So you had a simultaneous estimation of multiple air pollutants because there was cross correlations among the pollutants. Yeah, autocorrelation, absolutely. So yeah, we controlled for that.
Hi, I wanted to say that this is really great. I heard about your research before, but I'd never seen it, and it is really interesting. I have one question about the graph titled Inhalation and Speed.
Mm-hmm.
It shows what looks like a sort of parabolic, maybe exponential relationship, and I would almost expect that to be linear. Can you explain why it's shaped like this?
Yeah, there's two things going on. So you have this nonlinearity. So the aerodynamic drag force increases with the square of speed, and the power to overcome aerodynamic drag increases with the cube of speed. And so that's what's happening on the right side, is aerodynamic drag increases nonlinearly with speed. On the left side, you have that because it's in terms of volume per unit distance, you have essentially divide by the speed, divide the breathing rate per unit time by the speed. And so that's what's going on here. So at very low speeds, you have very long duration. And at very high speeds, you have a lot of power. And so it's nonlinear in terms of workload. It's also nonlinear in terms of, if you remember very early on, there was the ventilation versus workload, and that was nonlinear as well. So there's a couple of different nonlinearities going on.
I think you've definitely gone very in-depth and expanded on what other people have done in a similar research field. I'm curious, for looking forward, this is very bike-focused. Do you happen to have any ballpark numbers on what motorists' exposure rates are? And particularly because motorists, let's say on average, might travel 12,000 miles a year, whereas bicyclists might only do 2,000, 3,000 miles a year. So even if a motorist has half the exposure, they might have more total exposure. And like windows open, windows closed for motor. I've heard that like with the AC on, motorist exposure might be higher than one might expect. So are there any ballpark numbers on that?
Yeah, so it's a good question. We actually, Miguel and I did a paper on ventilation, for different ventilation now. Car ventilation, so windows up, windows down, AC, stuff like that. Out on Oregon 217, we collected a lot of data. And so, yeah, it's definitely an area of research. It actually is more research than Bicyclists that's existing out there. So motorists have, like I mentioned before, similar exposure concentrations depending on the conditions. However, they tend to be on larger roads, so on those facilities they have higher exposure concentrations. But for certain types of pollutants, the vehicle shell can have a pretty dramatic shielding effect if you have the vent closed. So the vent makes more of a difference than the AC.
It sounds like motorists in general might have more exposure to pollutants than bicyclists in some cases.
So, per unit distance, bicyclists are going to have more. But you're right. So per year.
Per year, because car drivers are driving so much farther.
Yeah, but there's another, and that's a good point, but there's another factor which is bicyclists, when they take long trips, become motorists in general. So it's not that people who are bicyclists only travel that much. It's that they only travel that much by bicycle, and then they have a lot of motorist miles logged in addition. So there's a lot of complicating factors in terms of if you look at one person's exposure over the whole year who uses a bicycle part of the year. I mean, that's a good question, which I haven't done that full net assessment yet. Yeah.
So you mentioned that weather also had a significant factor. Can you talk a little bit more about that? And would wind really have that much impact too, or like what about rain?
Yeah, wind is a pretty dramatic impact, and it's just dispersion. It just clears it out. So the higher the wind, the lower the concentrations. That happens on a regional level, and it also happens on a street scale level. Also, there's an elasticity of like 0.7 to background concentrations. So, there's just this concentrate in the whole city. The whole city has a certain level of concentration of all these pollutants, and it's elevated around roadways, but it's just kind of there. And for a major roadway, a major freeway, you're going to have a zone of influence 300 to 500 meters on either side of it that's being influenced kind of by this. You can think of like a pollution dome spreading out. So there's, and the size of that dome and the direction of it is going to be strongly wind dependent. And then there's also other pollutants, which what I haven't talked about. Ozone, for example, has a really strong temperature-dependent diurnal cycle, and so that's one where the effect of weather is going to be even more dramatic than we saw here for VOCs.
I was wondering how you think this could apply to peri-urban areas, especially heavily industrial peri-urban areas and suburbs and outskirts, where there are a lot of small industrial office parks and things like that. When your choices are essentially industrial zones or arterial routes, the answer is just not bike or two.
Yeah, so, well, starting at the end of your question, and this is something that's come up a fair bit, is that air pollution risks is one of many health impacts of bicycling. And if you look at the net effect of increase of physical activity, possible changes in crash rates, changes in air pollution exposure, it's even under pretty bad exposure concentrations, if you're in certainly if you're in a North American city, it's better to be biking than not biking, because the physical activity benefits outweigh these air pollution risks. So I wouldn't say the answer is to not bike. But in terms of if you have only arterial and industrial corridors, that's going to depend a lot on the corridors that you're talking about. And also, like I said, not all pollutants are industry-related. So here, VOC is strongly industry-related. Your CO exposure is not going to be that high on the industrial corridor. That would be a really complex. I can't say off the top of my head which one of those two routes would be lower or higher exposure than the other one, because there's a lot of pollutants to think about. Yeah. And the other piece of it is the dispersion, which I kind of mentioned there with the weather. Distance to industry, the amount of wind also has a big influence on how much the industry is going to affect the bike path concentration. Does that answer your question, Al? I think that went pretty good.